Math 1314, section IC1, spring 2022, Tyler Junior College. Homework 8.1, domains and asymptotes of rational functions. Video 8, finding where a graph intersects a horizontal asymptote. Now, if you were watching the previous videos, you've probably noticed this one is made in Zoom and not an older version that I use just making my phone. The reason for that is as I was reviewing the videos that I had made previously, they pretty much said everything that I wanted to say, except for one thing. Let me switch over to Canvas real quick just to show you what I'm talking about. So here's the 7 videos that I'd recorded previously, except there's one key thing missing from the discussion about horizontal asymptotes that's asked in your homework, and I'll show you what that thing is. This is question 9 on the homework 8.1, where you're asked to identify the horizontal asymptotes, which was discussed in the previous 2 videos in this module. But in part B, it says if the graph has a horizontal asymptote, determine the point, if any, where the graph crosses the horizontal asymptotes. And in the previous videos, I never discussed this concept. Well, I didn't want to throw away this question or the 2 surrounding it, numbers 8 and 10, just because of that part. So I decided to make a follow-up video, a new follow-up video to supplement this missing piece of information. So we're going to do precisely that in this video. So we're going to determine the point, if any, where the graph crosses the horizontal asymptote or asymptotes. Not sure why it's pluralized there. I just copied it from the homework because a rational function will never have more than one horizontal asymptote. There are functions that have multiple horizontal asymptotes. Well, you can only have 2, one for each end. But rational functions will not do that. But first, let's pass judgment, or let's determine what the horizontal asymptote is for this particular function. All right, recall that the horizontal asymptote can be thought of as the ratio of leading coefficients when the degrees match. Let me back up for a second. To determine the horizontal asymptote, we first compared the degrees of the numerator and the denominator. If they match, then the horizontal asymptote is y equals the ratio of leading coefficients. These degrees do match, so the horizontal asymptote is y equals the numerator's leading coefficient of -5 over the denominator's leading coefficient, which is an implied 1. So our horizontal asymptote is y equals -5. But to answer the question where the graph crosses the horizontal asymptote, and this is probably worth typing because this is the main idea that I want to focus on here. To determine where the graph might cross its horizontal asymptote, solve q of x equals the horizontal asymptote. And I'm kind of abusing the notation a little bit here, so let me back up and put a little bit more definitiveness to this. Determine where the graph of q of x, or whatever the name of the function is, might cross its horizontal asymptote of y equals, we'll say y equals c. So we'll give some things some names. We need to solve q of x is equal to c. In other words, all we have to do is put the function equal to whatever value determines the horizontal asymptote and then solve that equation. So we're going to solve that big ugly fraction equal to -5. Now, this might look more intimidating than it actually is, being an equation with quadratics and a fraction and all that jazz. But we have strategies for dealing with each issue here. For example, if we want to solve a rational equation, an equation with fractions, we have a strategy for that. The strategy is to multiply both sides by something capable of canceling all the denominators. Well, the only denominator is x squared plus 3. So we're going to start by multiplying both sides of the equation by x squared plus 3. On the left, the consequence is the x squared plus 3 cancels, leaving us the numerator, -5x squared plus 6x minus 2. On the right side, there's no cancellation, but we do invoke the distributive property. -5 times x squared is -5x squared. And -5 times +3 is -15. Now, This is a quadratic equation, and as a quadratic equation, we should probably get it equal to 0. Let's empty out the left side of the equation. Let's empty out the right side of the equation by setting up a cancellation for each individual term. Starting with the negative 5x squared on the right, we'll add 5x squared to cancel it, but then we have to add 5x squared to the left. And you're probably noticing that the x squared is going to cancel on the left also. That's a good thing. And to continue emptying out the right side, to cancel the minus 15, we'll do a plus 15 on both sides. Notice how I lined up my like terms, the plus 15 underneath the negative 2. Everything on the right side cancels to get 0. On the left side, the x squareds also cancel. That doesn't always happen, but I'm happy when it does. We're left with the 6x, and then negative 2 plus 15 is negative 13. Positive 13. Let me make sure I copy this down correctly, because that's a pretty nasty looking solution. Negative 5, 6, negative 2. Negative 5, 6, negative 2. It is copied down correctly. Make sure I didn't make any mistakes anywhere. Everything seems good because this quadratic equation is no longer quadratic, it's linear. And now I can just solve it by isolating the x. We'd start by subtracting 13 from both sides, making minus 13 show up on the right, then divide both sides by 6. And we end up getting x equals negative 13, 6. Now, the fact that we got x equals negative 13, 6 doesn't bother me too much, except we're asked for the point, which has an x and a y. We only have an x. I'm not looking too forward to what happens next, but it's something that we're capable of handling. It's just cumbersome, to say the worst. We need to figure out what y equals. And anytime you're finding a y and you have a function, you find that by putting the value of x into the function. Yes, we're about to put negative 13, 6 into our function. Buckle up, it's about to get a little bit bumpy. Let's start by rewriting the function and replacing each x with an empty parentheses in anticipation of filling it in with negative 13 sixths. Okay, now let's put negative 13 sixths in for each x. First thing I would do, or rather the next thing I would do, is I would square the negative 13 sixths on both sides. Leave everything else alone just for a moment. Let's do that. We'll go ahead and write everything else. Okay. First off, when you square a negative, it's positive, so that's gone. When you square a fraction, it's still a fraction. On the top, 13 squared is 169. And on the bottom, 6 squared is 36. Excuse me, I don't need the square down here. I am doing the square. 169 over 36. In fact, I don't even need that parentheses on the denominator because there's nothing being multiplied by that. All right, let's take it to the next page. All I did is write down where we were. Next order of business is to do this multiplication and this multiplication. Now, luckily on the second one, the sixes will cancel, so it's really only the first one that I have to proceed with caution. But we can think of the negative 5 as negative 5 over 1 and just multiply straight across the top and straight across the bottom. Okay, so in the first yellow box, the first off negative times positive is negative. In the bottom of the fraction, 1 times 36 is 36. And on the top, 5 times 169 is 845. Yes, I used a calculator. Plus, in the second fraction, the 6's cancel. So I'm just left with the plus minus 13, but plus a negative is the same as a minus. So just a minus 13. then the minus 2, and we haven't done anything on the bottom yet. 169 over 36 plus 3. Why don't we go ahead and combine the negative 13 and negative 2 to make it a negative 15 so that we can start making this expression look a little bit smaller, just making the fraction bar erased a little bit smaller. Negative 845 over 36 minus 15 over 169 over 36 plus 3. Let's take this to the next page and I'll show you what I think is the best move next. At this point, we have one of two options. Option number 1, get a common denominator for the problem in the top and make it a single fraction, and then do the same thing for the denominator. But if you do that, you're working with fractions. I would rather do the same move that I did at the beginning here. I would rather multiply so that I can cancel fractions. Now, here, we multiplied on both sides of an equal sign. But here, we can multiply on both sides of the big fraction. Let's multiply both sides of the big fraction by the least common denominator of the little fractions. Well, the only denominator on the little fractions is 36. So we're going to multiply both sides of this by 36. That will wipe out the little fractions, which frankly is not a bad thing. Okay, when we distribute the 36 across the subtraction problem on the top, when it hits the first fraction, it will just cancel the 36 on the bottom and leave negative 845. But the second half of the distribution is 15 times 36, which is 540, and it's being subtracted. On the bottom half, when we distribute the 36, again, when it hits this first fraction, it will cancel the 36 on the bottom and leave 196. The second half of the distribution, positive 3 times 36, is 108. And now we can just combine the numerator and denominator. Negative 845 minus 540 is negative 1,385. This is getting obnoxious. What did I say it was? Negative 1,385. Negative 1,385. And in the denominator, we have 196 plus 108, which is 304. And now there's the issue of whether or not this reduces. Well, I know I can't reduce it by 2 because the top isn't even. In fact, I can't reduce the top by any even number, because if I could, then the top would be even. So I can only reduce it by an odd number. But what can 304 reduce to? I'm going to do a thought cloud here, because when you're reducing fractions, you usually pick on the smaller number to look for options. Let's see how 304 breaks down. If we divide it by 2, we get 152. If we divide that by 2, 152 divided by 2 is 76. Looks like my cloud is not big enough. We can divide 76 by 2. And we will get 38. We can divide 30. Let me move this. This is getting, I don't want to say it's getting out of hand, but it's doing more than I thought. Let's break down the 38 into 2 times 19. All right, that's what I was looking for. The 135, the 1385 on top won't reduce by 2. So the only other factor that remains that it might reduce by is 19, and I doubt it will. 1385 divided by 19. Nope, it doesn't. All right, so the answer to it, does it reduce, is no. So what the heck is the answer to our question? What was the question? We were looking for where this graph crosses its horizontal asymptote, a point. We needed an X, and we just figured out the Y. So it looks like, believe it or not, our answer is negative 13/6 comma, negative 1,385 over 304. I gotta say, in all my years of teaching college algebra, that is probably one of the most obnoxious answers I've ever seen. I feel like something didn't go right, but I can check it because I'm in the homework, or at least I'm previewing it. The graph has at least one horizontal asymptote. The horizontal asymptote's equation is y equals negative 5. The crossover point, which they're calling it, I'm really wondering if this is what they were expecting, because if it is, I'm going to be very, very surprised. When I jumped into this problem, I hadn't done it yet, and I'm kind of surprised that it got to this point. Negative 1385 over 304. No way. Negative 1385 over 304. Surely this can't be what they were expecting. Of course not. Well, that's disappointing. But if you think I'm just going to say, I don't mind making mistakes. What I don't like is not knowing why I made them. So first, I want to see what this answer actually is, because I'm going to go in here and I'm going to define q of x equals negative 5x squared plus 6x minus 2 over x squared plus 3. Our horizontal asymptote is y equals negative 5. I'm not too worried about that. And the question was, where did it cross? And it seems like it crosses right here. Negative 2.167, which is negative, oh my gosh. I feel like a complete fool. Here's why. Can't believe I did all that. But it's okay to watch me struggle sometimes. How do we set all this off? We set it all off by saying the function is equal to the horizontal asymptote. In other words, we set it off. Let me go back here. We set this off by starting with, I need something that comes out to be negative 5. So I already knew what the output was supposed to be. I had the correct x. The y was going to be negative 5 because it was supposed to cross the horizontal asymptote y equals negative 5. So I feel kind of stupid. I do know that I had the correct x, because negative 13.6 is negative 2 1/6, which is that x coordinate. I recognize that as negative 2 1/6. I feel kind of dumb. I really feel kind of dumb that I didn't think about this problem in advance and I just jumped into it. But I'm still a little bit bothered about where I made a mistake. So stop watching the video if you want, but I'm going to keep recording it just so I can figure out where I went wrong. Okay. That looks good. Multiply both sides by multiply both sides by x squared plus 3. Looks like everything happened correctly. I'll highlight where I'm looking so you can kind of follow my train of thought if you're watching. All right, this canceled correctly, so I'm not too worried about that. This, all of this seems to have worked okay, because when you distribute the negative 5, you do get this. You do get this. Draw, please. You do get this, so I'm not too worried about that. Did I bring down the left side correctly? Let's get rid of that. Negative 5x squared plus, that looks correct. These are the correct moves to cancel. Did the same thing there. The 5x squared cancels, 6x comes down. Well, I know the negative 13.6 is right. Well, I don't know why I'm wasting my time looking at that. Again, right now I'm just trying to figure out where I went wrong. Our function was negative 5x squared plus 6x minus 2, correct? Yes, over x squared plus 3, that is correct. I put a negative 13.6. Did I bring everything else down? Negative 5 came down correctly, plus 6x became plus that, minus 2. X squared plus 3 came down correctly. 13 squared is 169, I know that. So that part's correct, and that part's correct. The negative 5 came down, the positive 6 came down, the minus 2 came down, plus 3 came down. All right, all this looks good. Let's make sure I didn't botch it up when I move to the next page. Everything still looks good, going back just to make sure I didn't miscopy something. Okay, let's focus on, did I do that part correctly? 169, using a calculator, times 5 is 845, but negative. Here the 6's cancel, leaving a negative 13, minus 2. Nothing happened there. Negative 13 minus 2 is negative 15. Everything looks okay there. Making sure I copied it correctly. Found it. Found it. Found it. Oh my gosh. Some of you may have been yelling at it. Had a temporary case of dyslexia. The number down here was 169. Now it's 196. Man. But now that I know where I messed up, I'm going to finish this by making the necessary changes. Okay, that should have been 169, which means this should have been 169, which means this should have been 169 plus 108, which is 277. And let me guess, 1385 divided by 277. Y'all gonna watch this part. 1385, oh, excuse me, negative, divided by 277 is exactly negative 5. Doesn't matter how good you think you are. Doesn't matter how good you think you are. If you are not careful, you can make the most casual of mistakes and really botch things up. I'm just cleaning up this so that it'll be correct when I save the PDF. I do want to make a quick comment though. We should have known the y coordinate of the intersection point was going to be negative 5, since we started with q of x equals negative 5. I feel so dumb that I didn't even think about that. I was so worried about, oh, I need a y value. I got an x. Let me cram it in the function, see what happens. But that just goes to show, once again, doesn't matter how good you are, how good you think you are. If you rush, don't pay attention, don't focus. Sometimes you can make a task harder than it has to be.